All right. So let us begin. I'll begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you would just guide our steps, help us to understand more about the Mobius transformation, all these things, and just allow us to just enjoy the beauty of your creation. Lord, in your name I pray, Lord Jesus. Amen. So, a little bit of fun abstract algebra. Let's get it out of our system. So, the Mobius transformations and in fact it's a group. All right, and so let me be more specific. We have f of z is equal to, az plus b over cz plus d, right? And we described how provided that we have ad minus bc not equal to 0, right? And what else did I do? I worked out the formula for the inverse, didn't I? And wouldn't you know it, I don't have that formula on me. Can you guys tell me what the formula we found for the inverse was? What was f inverse of z?
1 over a. It
was negative d plus b over cc minus a.
Yeah.
Excellent. So let me propose something. Let us say that psi of f is equal to a, b, c, d. Right? This would be an element of GL2C. So what is GL2C? Well, GL2C is the set of 2 by 2 invertible matrices with complex coefficients. The reason that this image is into GL2C is because the determinant of the matrix I wrote is what? It is AD minus BC, right? Which is not equal to 0, which is tantamount to this mapping psi being a mapping into the general linear group of 2 by 2 complex matrices. Okay, so what is psi of f inverse then? What do you got?
The identity matrix?
No.
B minus D,
Mm-hmm.
D, C
Minus D, what'd you say?
B.
B's the same? Oh yeah, it is. Are you sure that was for this one? I had the letters the same? Okay, cool. I mean, I think it was. And then so, C is still C? Funky. And what we got? Minus A. Oh man, I was hoping. Ah, rats. Huh, well that's funny. This is equal to, minus 1. Well, it's equal to minus AD minus BC times 1 over AD minus BC DA minus B minus C. The reason I wrote it that way, which is kind of weird, I have my reasons. This right here is the inverse of the matrix, right? So the 2 by 2 matrix inverse formula. So let's see here, how can I say this? So in other words, we have the identity that psi of f inverse is apparently equal to minus the determinant, well, minus AD minus BC times psi of f inverse, which is not what I was hoping for. I thought this might be an isomorphism, but obviously it's not. Right? If this was an isomorphism from the set of Mobius transformations to the set of 2 by 2 matrices, then I would have just got that the isomorphism of the inverse map is the inverse of the, you know, I could invert the image just the same. I wouldn't get this extra product of the determinant formula here, right? And the minus sign is even more annoying because I was hoping, oh, well, if there's a determinant formula, maybe I could specialize my attention to the case that the determinant is 1. You know, I could specialize my attention to these kind of transformations, but with determinant 1, and then that would give me, you know, an isomorphism in that context. But that minus is messing that up even. So, if there is a isomorphism, it's something more subtle than this. Oh well. But there's something else that you can see here, which is kind of neat. So it's not an isomorphism apparently. Oh man. Does it at least map the identity to the identity? Well, I mean, psi maps, like psi of, so if we look at f of z equals to z, right? Then what's psi of f? So a equals 1.
0, 0, 0.
So a equals 1 and d equals 1, right? For z, this map.
Oh, yeah.
So that gives us,
Yeah.
so that, I mean, at least it's a homomorphism. Huh. All right, well, either the group structure of the Mobius transformations is not simple composition of functions, or I don't know what's going on here. I'm annoyed. Let me go on. The other thing to notice, though, let me show you more before I give up on it entirely, because this is also a neat calculation. What if we take 2 of these? All right, so az plus b over cz plus d, and say g of z, alpha z plus beta over gamma z plus delta, and you compose these. What happens? We have f composed of g of z. How's that work out? So we'd have like a times alpha zeta plus beta over gamma zeta, z plus delta plus b divided by a times alpha z plus beta divided by gamma z. I never say z. Why am I saying z? Plus delta plus d. And then clear out your denominators. All right, anyway, a alpha z plus, wait a minute, is that right? B times, oh rats, sorry, alpha z plus beta all times a plus, just hold on a second here, b times gamma z plus delta divided by, why wouldn't that be that's a good question. I will not hold off. Your question is excellent, which is why in the world did I not write C there? And the answer in short is women. Fallen man. It all goes back to Eve. Let's see here. So C, it's been a while since I said that. It feels good. It feels dangerous though these days. It feels dangerous. D times, they don't teach you that in Convo, do they? Let's see here. No. Anyway, so put this all together. You got yourself a alpha plus b gamma times z, and over here you got yourself a beta plus b delta, right? Divided by, this should have been a homework problem, c alpha plus d gamma, but you know, we don't have like any kind of linear algebra prerequisite for this, so it seems kind of sketchy. C beta, I know, there's no Math 200 prerequisite either. Obligatory. This is why we can't have nice things. Is this material too good for you?
He has something important to do.
Uh-huh. No, I don't want details. I don't want details. I've learned with a person like Anthony, you do not give him the bully pulpit in this situation, because you may regret it. So if we look at the matrix A, B, C, D times the matrix alpha, beta, gamma, delta, you get A alpha plus B gamma, C alpha plus D gamma, and A beta. If you haven't had Math 221 yet, well, you're welcome. B delta and C beta. You can take this with you to Math 221 when you take next, D delta. If I didn't do that wrong. Hey, I'm teaching Math 221 next semester. You want to come join us? Anybody? I'm hoping and praying I'm teaching 321 next fall. So we'll see. But you notice that is that, right? And for instance, this is this. Yeah. Did I make a mistake?
No. Sorry, do you mind if I ask a question about the left over here?
Oh yeah, if I made a mistake, I would love to know about it.
No, on C of F inverse, if you negate both the numerator and the denominator, you end up getting rid of the negative sign, I think. And so, therefore, if you restrict it to matrices of determinant 1, you could construct a nice multiple, unless I'm not seeing something. Like if you expressed F inverse of Z as dz minus B over A minus CZ.
Say what you said. You said express F inverse of Z as what?
Sure. As dz minus B over A minus CZ. Just multiply both numerator and denominator by
Oh, so minus CZ plus A?
Yeah.
Okay.
And then expressing that in matrix form, you do get,
So that maps to,
yeah.
oh. Oh. Interesting.
Which is the inverse of the matrix for F of Z, but does that also mean the mapping is not well defined?
Oh.
Oh my gosh.
Yes, it does mean the mapping's not well defined. Unless we identify antipodal points.
Is this a new theorem?
No, remember Becca, remember I told you something about deep, dark water off the shore?
Yes.
We're getting into that now.
Oh.
This is what I was talking about.
Yes, sir.
So I think you're right, and I think to make it well defined, you need to work on like something that identifies the plus and the minus of the matrix. And that's something like projective space. Projective space does something along this. It like basically identifies antipodal points on a sphere or something like this. But anyway, now I'm getting way, way off track. But thank you.
Sorry.
I think that's it. I think that's the issue, in fact. And also why I really should have spent, 15 minutes on Wikipedia poking around before I talked about this in class, but oh well, so sorry. Anyway, my point to you is there's obviously like a connection between the group theory of 2x2 matrices, complex entries, and these Mobius transformations. However, I think I've also convinced you that it's subtle. It's not quite just, yeah. Yes, Jeff?
You highlighted only those two, but like it's all four of them.
Right, yeah, it should match up. I just particularly those and here. This one is that one, right? And this guy is that guy, so yeah. So the composition as it relates to matrix multiplication is far more forgiving. Whatever's going on with the the inversion's fussy. Okay, anyway. Let me go on here. So let's look at some examples. I have an example for us. Example 1. Suppose we have the disk. We can take this disk here. I got 1, I got I, and I've got -1. All right, and I'm going to kind of think of this disk oriented, the boundary oriented in this way. All right, so like that, and I'm going to map it. I'm going to map the interior of this disk. I'm going to map it to the upper half plane as follows. Put a 0 here. I'm going to put a 1 here. I'm going to put a -1 here just to keep track of things. And what I want is to find, my claim, guys, is that if you pick a disk, an open disk, well, a closed disk rather, pick a closed disk, I can find a Mobius transformation, a fractional linear transformation, which will map me from the disk to the closed half plane. Uh-oh. I put it too far from me, haven't I? Let's see here. And the way this works is, if we think about it, if you're going first you're going to 1, then you get to I, then you get to -1 as you go around the circle. I want that to, I'm going to orient it this way. So if you can imagine yourself a little dude walking along this curve, then above is on your left. So if I orient this line this way, then the inside of the half plane it's defining is up there. And so I want to send 1 to -1, I want to send I to 0, and I want to send -1 to 1. All right? And my claim is that I can do this with a Mobius transformation. All right? And I'm going to show you how to construct it through just simple means. And so just here's how you do it. Now, you could ask the question, well, how do you do it in general? Like, how do you find a fractional linear transformation, a Mobius transformation that goes from one set to another in general? And the answer is, it's complicated. But there are some general rules that we can look at. But for something as simple as this, let me show you what's simple first, and then we'll try to get into what's more complicated as we go on here. But I'm going to write down A times, well, hey, I want to go to 0. I love this middle one, I mapping to 0. That's nice. That's real nice, because that means I can just put a z minus I up in here, right? And then downstairs I've got bz plus c. Now I say, okay, well, scratch that. We're just going to do z minus I over az plus b, because by golly, why, I'll put some tildes on here. There you go. Okay. I'm redefining my constants, because why not? I might as well just keep all my constants in the bottom. I don't need that upstairs constant for any reason. Okay? Then what? Well, Okay, so then I also need what? I also need f of 1, which by the way would be 1 minus I over a plus b. I need that to equal minus 1. And I need f of minus 1 to be minus 1 minus I over, well, b minus a to equal 1. So lo and behold, I get the equation a plus b is equal to I minus 1. And I get, b minus a equal to minus 1 minus I. We can solve these, right? Yes, sir.
Negative a minus b?
Negative a plus b if you like.
Well, we're talking about the top line.
Yeah, the top line.
A plus b equals I minus 1, but f1 equals 1 minus I over a.
I have spoken.
Oh, but it equals negative 1.
Yeah. Sorry. Remember when The Mandalorian was interesting? I do. I remember. Like the first season, the I have spoken guy, that was interesting. 2b equals to, I add these, the a's be canceling, and then the minus I and the I cancels, you get minus 2. Apparently b is equal to minus 1, hooray. And if on the other hand I subtract, I get 2a is equal to, 2i. So apparently a is equal to, I. Unless I made a mistake, which is, of course, possible. No, that's what I got earlier today. That's good. So f of z, lo and behold, here it is. You got your z minus I divided by, apparently, iz minus 1. And there you go. That is the fractional linear transformation which maps that open disk, well, closed disk rather, to that closed half plane. Now there's a theorem. Well, there's other things I should show you about the Mobius transformation, one of which I shouldn't have buried the lead here. What's the derivative of the Mobius transformation in general? Like if I calculate df dz, what do you get? I get what? I get a times cz plus d minus az plus b times c divided by cz plus d squared by yield quotient rule. And that, I sure hope it simplifies. What do you know? AD minus BC over CZ minus CZ plus D squared. Aha! That is non-zero. Except where? It's not equal to 0 for z not equal to infinity. I suppose I'm slightly worried at the pole. What happens at the pole, right? Okay, fine enough, fair enough. And maybe z equals to minus d over c. Maybe that's a problem too. I mean, if that happens, we're dividing by 0, it's infinity. At least we can't say that the value of the derivative is a non-zero complex number, right? It would be infinity there. What does this mean? Do you guys remember? What's the situation if the complex map, if you've got a complex map, right? You got z-plane, you got w-plane, right? You got a pair of curves, right? And their images, right? What's the situation? If the derivative is non-zero, what do we get to say? Do you remember? So it's a holomorphic map with a non-zero derivative. It has the what? The conformal property, right? So this angle and that angle have to match up. All right? So that's one of the things we can understand about the fractional linear transformation is it's a conformal transformation away from what? Away from infinity and the pole. Infinity and the pole, funky stuff can happen there, but elsewhere it's conformal, which means, among other things, one of the useful things that you can do in your construction of maps is if you have in your domain the intersection of two perpendicular lines, then it has to map to perpendicular lines in the image. That is a very, very powerful observation for certain examples. And I remember from last time I taught this course vaguely that there are problems that I get absolutely stuck on unless I use that intersection principle. Don't ask me which ones. Okay. But I want to point out something else, something just really concrete. I claimed that, well, I haven't claimed this yet, but the other thing we can claim is that a fractional linear transformation will map the interior of the set to the interior of the set, keeping in track of the orientation. So like, if this is the boundary of some set, if this is the boundary curve of some set, right, the original circle here, then the inside is in here, right? Because if you imagine yourself a little dude walking around, the left is the interior of the disk. Likewise, the interior is up here. Let's check me on that. What's a point in the interior? How about this? How about 0? What's f of 0? Well, we've got 0 minus I over I times 0 minus 1, also known as I. So where does it map to? Up here, I. So this verifies my claim. I mean, obviously it's not an arbitrary point, but you could take an arbitrary point inside this disk, all right, and show that under this mapping, it has an imaginary part which is positive. This you could prove. This you could verify. This would make a rather onerous homework problem. Don't worry, I'm done constructing your homework already, so you're safe. All right. The only place I could put that would be the final. Sorry, is it too soon? Anyway, yeah. Any questions? There is this sort of universal trick that you can use to solve these fractional linear problems, where you can use what's called the cross ratio to set it up. And I was trying to find the formula for it before class, and I couldn't get my paws on it. I don't have it written down, so I'm going to have to look it up if I put it on the board. I probably should. I have another example for us, though. Let's look at the example. In my personal experience, using the cross ratio, yes, it's right. Yes, it is foolproof in the sense of like here's how it works. You decide the transformation you're looking for. You want it to map. Let me just look up the stupid thing. So here's the deal. You're taking an input, Z1, Z2, Z3, and you want to map it to a specific set of points, W1, W2, W3. All right? These are ordered. The ordering matters. Different order, different map. Okay? But you can find the fractional linear transformation, the Mobius transformation, F, which does that by solving. Goodness gracious. If I just make it up, I'll be wrong. I'll tell you what, let me take a guess. I'm going to try guessing, and then we'll check my guess. How about that? Z minus Z1 W minus W1 and then I want to say something like Z1 minus Z2, Z2 minus Z3, Z3 minus Z2. This might be the pattern. Oops, W's over here, all W's. All right, and tell you what, guys, I'm gonna check it. Oh, wait a minute, no, that's not it. That's nonsense. That ain't gonna do it. That is not it. What should I do? Maybe this is supposed to be a 1. No, that can't be it either. Rats. 3 and 1. None of these things should automatically simplify to 1 or -1, okay? So I can't have like a replica. Maybe this. Nothing here simplifies, right? Come on. Come back to me, computer. Huh. I guess this has a, this is also studying like geometry. So you can ask, oh man, that's not the one I want. Let's see, so what do I have? Phooey. Let me write down the one here. We got 3 minus 1 over 3 minus 2. 4 minus 2 over 4 minus 1. I'm gonna have to change the numbering to match up with what I got on the board. That's why I had to write it down. So I want to think of, let's just think of 4 as x, like think of 4 as x. Well, what I really want to think of x4 as z, think of x3 as z3, think of x2 as z2, think of x1 as z1. Does that match up the pattern? All right, so if I trust Wikipedia, and I think I do, we should do z minus z2, and then z minus what? Z minus z1, and then let's see over here, z3 minus z1, and z3 minus z2, and then it's the same over here. So w minus w2, w minus w1, w3 minus w2, and w3 minus w1. Did I get, does that, you guys tell me if the pattern looks right to you. So the claim is you can just write this down and solve for w. That gives you the formula for the FLT, which maps this triple to that triple. And the book that you guys don't like, understandably, because it's not a great book, but it's got great homework problems, and it's cheap. Woohoo! The book has a pretty decent explanation for why these things are true, why those have to be equal. For the FLT, which does this, for the Mobius transformation, which does this. Let's see here. So the claim is, like, let's foolishly try this on my example 1. I have what? You guys are gonna have to help me out here. Remind me what triple I'm mapping. What to what to what? So it's 1 comma what, comma what?
I negative 1.
I negative 1 to the,
Negative 1, 0, 1.
all right. So this is my Z1, Z2, Z3. This is my W1, W2, W3. All right. All right. So we've got Z minus I divided by Z minus 1, parentheses, times minus 1 minus 1. Well, that wasn't too bad. 3 minus 2 minus 1 minus I. And that's equal to W minus 0. Well, that's a relief. And W plus 1 times a parentheses. W3 is 1 minus W1, which is plus 1, divided by W3, which is 1. Well, look at that. So this is 2. That is, so I can rewrite this Z minus I over Z minus 1, all right, divided by 1 plus I is equal to W divided by W plus 1. And then you just need to solve for W. Allegedly, I'm kind of scared to do it. You'll get my formula. Yes?
Is it negative 1 on the left side?
What I did was I absorbed the minus down here, which gave me a 2, and another 2 here, which I canceled. And so, all right, great. Then you get W plus 1 times Z minus I is equal to, W times Z minus 1 times 1 plus I, which gives us WZ. WZ. Anyway, I don't want to solve this. I mean, this is not interesting. You should be able to solve it and get the example 1, all right? If it doesn't work out, I'd like to know about it, though. Yeah? So anyway, what I'm trying to tell you, for me, the cross ratio is a weapon of last resort, and I try to solve it any other which way before that. You can put infinity into the cross ratio, but you have to understand it in a limiting sense, all right? I think there is some discussion of this in the textbook, so you can look at there. Here's another one. Suppose, example 2, I'm gonna map the disk this time, and I'm gonna put I up here, so the unit disk because I'm lazy, minus I, and 1 over here. And I'm going to think about them in this order, all right? And I want to find a transformation. I'm going to call it T this time. And T is going to map over here to infinity, and then eventually you'll get to I, and then eventually you'll get to 0, all right? So in other words, I want T of minus I equal to infinity. I want T of 1 equal to I. And I want T of I equal to 0. All right? And I'm gonna do it with a fractional linear transformation. All right? Can we do it? Can we map inside here to like over here? So if we, I go minus I, then 1, then I. Likewise over here, I start infinity, get to I, go to 0. At least if I can imagine myself a little dude walking down this direction, that's my left. Okay? So, yeah. So what's the formula? And so, like, once you learn about the cross ratio, it's awful tempting. It's awful tempting because you know it works. But on the other hand, do you love algebra that much? Because I hope you start to appreciate that the algebra involved here is non-trivial. It's very easy to make a mistake in the midst of all that. So if you can just write down the formula by some like general principles, it's much easier. Like, let's see here. So, oh, look at that. That happened again. So we've got T of Z is equal to Z minus I, right? Over AZ, oopsies, AZ plus B, right? Ah, but this, I love this. This is even nicer. Like, look, this is like the nicest kind of situation. See this right here? Oh, that's wonderful. What does that mean? That means we can just keep one scale factor out in the front. We put our Z minus I to get the 0 upstairs, right? And we put our Z plus I downstairs to make the thing blow up when we get to I, right? So we put the pole at minus I, and this will satisfy the two blue circle things. And to get the other one, just plug it in. So T of 1 is A times, well, 1 minus I over 1 plus I. Yeah, exactly. A is, and that's equal to, what is that equal to? Oh, I, right? So A is equal to I times 1 plus I over 1 minus I, which I'd like to clean that up. I'm going to multiply by 1 plus I over 1 plus I. And that will give me I times, 1 plus I squared is actually 2I, isn't it? Notice that 1 plus I squared gives me a 1 squared plus 2I plus I squared, but 1 plus I squared is 0, so we just get 2I when we take 1 plus I squared, right? And so there's the 2 downstairs, and so this simplifies to minus 1, I think. Yeah. So my fractional linear transformation is in fact equal to, well, however you want to write it. I could write it I minus Z over Z plus I if you like. I'm absorbing the minus 1 as a vain attempt to confuse the students. Possibly successful, I don't know. And let's check it. Let's check it. If we're right that the interior of the disk is mapping to the right half plane, if I look at 0, where should it go? It's T of 0 here. I over I, which is 1, which is about right here-ish. So that's a good sign. I mean, that does not prove, obviously, that the disk maps to the entire half plane, but you could prove it. All right? You could prove that on the final. Okay, I'm just joking. I don't want to grade that either, right? But think about it, how you'd prove that. All right, so I think I've showed you enough of this that you kind of get the flavor of how we're going to calculate fractional linear transformations. There's 10 homework problems on it or something, so after you do all those, you will be totally bored with how to find these, all right? So whatever I haven't covered in class, the homework will beat to death for sure, all right? And I'll help you with those if you get stuck. I wasn't intentionally trying to choose difficult ones, but you know how it is. This is lovely, but why are we doing this? Besides just that it's really cool math, like is there a deeper reason? Well, there is. Let me show you something here. So you guys remember the discussion of Laplace's equation, right? Remember Laplace's equation? Check this out. So if here I was to write down, and I guess if we're going to think of this as the W plane, so we have what? Over here, we basically got, this is V, right? And this is U, right? Over here, we've got, you know, the y-axis and the x-axis, right? So the z-plane, the w-plane. And I could write down over here, I could write down psi of w equals to 2 over pi inverse tangent of v over u, right? Can you recognize what that is? What is that? That's nothing more than, you know, 2 over pi times the imaginary part of, well, what? The log of w, right? Because the log of w is the natural log of the modulus of w plus I times the argument of w. But the argument of w is given by the inverse tangent of v over u as long as we're in the positive, the real part being positive for the u plus iv plane, right? W is equal to, and if you forgot, w is equal to u plus iv, okay? So let me explain what this is. This solves psi uu plus psi vv equals to 0 on the half plane, right? It is the imaginary component of a holomorphic function, therefore it is a solution to Laplace's equation. But it's more than that. It's a solution which has a very interesting, well, maybe very is too strong, but it has a very particular behavior on the edge of the half plane, right? Let's talk about how it is. So up here, you've got angle what? Theta equals to pi over 2, right? Down here, you've got theta equals to minus pi over 2, right? So if you look at that and appreciate what's going on here, we have all up in here, we have psi equals to 1. And all down here, we have psi equals to minus 1. Okay? Are we agreed? I mean, it's not especially exciting, but that's the situation. And let us remember, okay, let's try to color code it here. Let me use green for this piece instead of orange. You guys tell me what part of the circle corresponds to the you know, which part of the circle corresponds to which part of the imaginary axis? The green part, let's see, infinity, where does I is, my bad, minus I is where the infinity is. So this went to infinity, right? And this went to 0, is that right? So to go from infinity to I believe this part maps to the upper half, and this part, wait a minute, I'm a dummy. 1 maps to I, right? So it's going to be, my luck, I'm an idiot, this way, right? Obviously that way. Duh. Duh. Duh, 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 duh. So this half of the circle maps to the, if in doubt, try a point, check yourself, right? This point right here is -1. What's t of -1? I minus 1, right, over -1 plus I, which is -1. Oh! Whoa! What just happened? Look at that. That wasn't intentional. We found the fixed point. Oh yeah. So right there, that's a fixed point. It went mapped to itself. Yeah.
Did it?
Did what?
Did it?
Did I do something wrong? Hmm? Oh, you mean it should be this point again?
No, I'm saying like
Aw, man.
I minus 1 over
Son of a gun.
I minus
That's not right. I minus 1 over...
I minus 1.
Ah, I forgot. I got tricked, didn't I? So what was this? You said it's I minus 1? Wait a minute.
Well, that is what you just wrote down.
-1 plus I?
Minus 1 plus I.
Oh, rats. It's 1, isn't it? What? Oh man. I did something wrong. What did I do? Look at, come on guys. You should be +1, dummy. Me, not you. And then -1 plus, all right, great. And then this is what? If this works out to -1, that's pretty funny. I think it works out to -I actually. So this is I plus 1 times I plus 1 over 2, which is 2I over 2, which is I? Did I do something wrong again? Seriously? Oh, come on.
Should be a -2 in the denominator.
Yes, thank you. All right, so finally, my heart was in the right place, even though I pictured it correctly, but I miscalculated now enough times. Enough miscalculation, let's go on. All right. We now have it pictured properly, yes? Great. So what is this? First of all, this solution doesn't really have too much to do with the fractional linear transformation involved, right? But here's the cool thing, is we can use this fractional linear transformation and this quote-unquote template solution on the half plane to build a solution to Laplace's equation over here, which puts a boundary value of 1 here, let's say 1 equal to phi, and phi equals to -1 over there. What is that? Phi of z equals to what? We simply do this, psi of t of z. Now, of course, I need to be more careful. I need to take like the, I think the real part of it or something, because t is complex, of course, but let's see here. No, I think this makes sense. This will be a real solution. But the reason that that's a solution to Laplace's equation is because this is literally the well. Anyway, let me just write it down here. So phi of x plus iy, what's it equal to? It's equal to 2 over pi, basically the principal argument, if you will, of I minus z over z plus I. which, if you work it out, is 2 over pi times the principal argument of, the way that works out is 1 minus x squared minus y squared plus 2ix divided by x squared plus parentheses y plus 1 squared. Which specifically is equal to, in our context, 2 pi inverse tangent of 2x divided by 1 minus x squared minus y squared. Because when you calculate the area, listen to me. When you calculate the angle, the denominator doesn't really matter. It's really based on the ratio of the y, the real and imaginary components, which both share the same ratio, same denominator. Look at how this works. What happens as you approach the unit circle with this formula? The denominator has what? A division by 0. When x is positive, it's going to plus infinity. When x is negative, it's going to minus infinity. Inverse tangent of plus infinity is pi over 2. In other words, you have the boundary value of 1 on the right half, and you have the boundary value of minus 1 on the left half. This is the technique of conformal mapping. What conformal mapping does, its idea is to find, basically, you collect a bunch of nice solutions to Laplace's equations on really simple spaces like half planes, sectors, annuli. We'll look at those next time, all right? So you get this like set of really nice, easy solutions to common, like really simple geometric shapes, right? Then you learn a bunch of complex mappings, which take those simple shapes and bend them and twist them into more complicated things in a way that you understand. And then what you can do is you can set up complicated boundary conditions on the simple shapes and simply compose with the fractional linear transformation, or whatever complex transformation it is that maps your complicated space to the simple template space. And by this simple composition trick, you write down solutions in the complicated space based on your complicated solution on the simple space. This is the technique of conformal mapping. I don't know about you, but I'm not sure I would have been able to find this solution on the disk if I had been asked to solve Laplace's equation on the disk with subject to those boundary conditions. I'm not sure I would have come up with this, personally. All right, so solving Laplace's equation, well, who cares about that? Well, Laplace's equation is a lot of things, which we'll talk about next time. But the rest of class, I want to spend talking more about just the beauty and like coolness of the, the Mobius transformation. I still think we have some time, right? Yeah, we're good. We have enough time. So I happen to have this thing here, which is a sphere, all right? It's a sphere that's 3D printed, and this is a hopefully working pen light. Oh man. Yes, all right. Now, we are thankfully in a room with switches. Oh yeah. And I'm not sure the camera will pick this up, but we'll find out. So check this out here. Can you guys see it? So I put the pen light at basically the north pole of the sphere. And if you look, once your eyes adjust to the light here, or lack of it, you should be able to see that we have